One generation ago, Google's best open model scored 20.8 on AIME, the American High School Maths Olympiad. This year's model scores 89.2. Same lab, same size class, 12 months. I checked that twice. That's Gemma 4. But the score isn't the interesting part. The interesting part is that the smallest model in this family fits on a phone, and the strangest one got there by deleting half its own architecture. Let's actually read the paper. 5 models, 2.3 billion parameters, up to 31. 4 dense. 1 mixture of experts. All of them natively multimodal, text, images, and audio in the same stack. All of them Apache 2.0. Weights on your disk. No API key, no rate limit. 150 million downloads in. Gemma stopped being a research demo a while ago. Now, the 2 small ones come with a footnote. E2B is not a 2.3 billion parameter model, it's 5 billion. It borrows a trick from Gemma 3N called per-layer embeddings, a chunk of the weights that doesn't have to sit in fast memory alongside everything else. 2.3 billion is what actually has to be resident, and that's the number that decides whether it runs on your phone. The paper calls this effective parameters, which is a marketing term that's unusually honest. The 5th model is 26BA4B, 26 billion parameters total, 3.8 billion active per token. A small router looks at each token and wakes up a few experts. The rest stay asleep. You pay memory for all of them and compute for a handful. How many experts? What top K? The report doesn't say. Hold that thought, we're coming back to what this paper leaves out. Underneath, all 5 are the same decoder-only transformer you already know. RMS norm before and after every block, plus QK norm on the queries and keys. That is a lot of normalization. It isn't tidiness. Bounded activations are the reason the quantisation at the end of this video survives at all. 1 tokenizer across the family, 262,000 entries, shared with Gemini. Remember that number, it comes back. Here's the thing that actually stops a model running on your hardware. It isn't the weights. When a transformer generates, every layer stores the keys and values of every token it has already read, so it never recomputes them. That's the KV cache. At 1,000 tokens, it's a rounding error. At 128,000, it's the reason the thing won't load. The weights are your suitcase. The KV cache is everything you buy on the trip. Gemma 4 attacks it 4 separate times. Let's count them. Most layers don't need the whole context, so the layers alternate. 5 sliding window layers that only see nearby tokens, then 1 global layer that sees everything, 5:1. E2B runs 4:1. A local layer only ever caches its own window, which means almost all of your long context memory collapses into a small number of rare, expensive global layers. And a small number of expensive layers is a very attackable target. In those global layers, Gemma 4 stops computing a separate value projection and reuses the keys as the values. 1 tensor in the cache instead of 2. Yes, that's allowed. No, the paper does not apologize for it. Position goes into attention through rope, rotating pairs of dimensions at different frequencies. Global layers switch to p-rope, rotate only a quarter of the dimensions on a base frequency of 1 million. Local layers keep standard rope at 10,000. The logic is nice. A narrow sliding window has no use for million token wavelengths. Cuts 2 and 3 together. The global KV cache drops 37.5%. This one is only on the small models, and it's blunt. Reuse the same KV across multiple layers. 20 of E2B's 35 layers. 18 of E4B's 42. Here's the payoff, and it's the number I'd keep from this whole section. A Quantist E2B holding 32,000 tokens of context spends about 50 megabytes on its entire KV cache. 50 megabytes. That's 1 photo. So it's cheap to run. How does it see? The classical answer, used by 4 of the 5 models, is to bolt an encoder on the front. Vision is a VIT, chopping the image into 16 pixel patches. The small models carry 150 million parameter 1, 16 layers deep. The 31B and the MoE share a 550 million 1, 27 layers. 2 details in here are worth stealing. 1. Real images aren't square. So instead of cropping to a square and throwing away your composition, Gemma 4 resizes while mostly preserving aspect ratio, then rounds to a whole number of patches. 2. Those patches get pooled 3 by 3 into soft tokens, compact vectors the language model reads like words, and you pick the budget, 70, 140, 280, 560, or 1120 tokens per image. More tokens, more detail, more compute. Your call. The paper demonstrates all of this with an otter in a spacesuit. 72 patches, 8 soft tokens, 1 otter. I did not have that on the card. Audio. Sound is cut into 40 millisecond chunks, turned into MEL spectrogram features, and pushed through 2 downsampling convolutions and 12 conformer layers, a recipe out of Google's Universal Speech Model. 305 million parameters, 55% smaller than Gemma 3N's, and it transcribes better than the thing it replaced. Both encoders stay frozen through pre-training. Both hand the model continuous vectors. No vector quantization anywhere. Which brings us to the model I actually wanted to talk about. The 12B has no vision encoder and no audio encoder. Not a smaller one. None. For images, those 550 million parameters become a single matrix multiply. Raw 48 by 48 RGB patches project straight into the embedding space. 35 million parameters doing the job of 550. Spatial layout survives on 2-dimensional coordinate embeddings added to each patch, and 1-layer norm on the way out. That is the entire vision system. Audio is more radical. The conformer stack isn't shrunk, it's deleted. Raw 16 kHz audio, cut into 40 millisecond chunks. Each chunk is 640 numbers. Those numbers go straight into the model. No positional encoding. Audio already arrives in order. The obvious question, does it work? On FLIR's speech recognition, the encoder-free 12B lands word error rates between 5 and 8% across languages, 6.3 on English. That's competitive with models still carrying a dedicated encoder. And Google's own line, the 12B gets close to the 26 billion MOE on standard benchmarks at less than half the memory. One transformer that reads, sees, and hears in one stack. Nothing separate to compile, nothing separate to quantize, no memory fragmented between subsystems. If you've ever tried to ship a multimodal model, that last sentence is the whole pitch. Next bottleneck, speed. A transformer emits 1 token per forward pass, and every pass drags the entire model through memory. That's the tax. The standard fix is speculative decoding. A small fast model drafts several tokens ahead, and the big model checks all of them in a single pass. When the draft is right, you got several tokens for the price of 1. When it's wrong, you bin it, no harm done. It's an intern writing the first draft and a senior editor reading it. Very cheap, as long as the intern is good. Normally, you have to go find or train that drafter. Gemma 4 ships one inside the model, a multi-token prediction head, trained alongside it. And here's the part worth the diagram. The drafter never rereads the conversation. It takes the main model's last layer activations, adds fresh token embeddings, and cross-attends straight into the main model's existing KV cache. So it has no pre-fill of its own, nothing to warm up, it can draft as far ahead as you'll let it, and it's tiny. 4 transformer layers, 3 local, 1 global, at hidden size 256 on the small models, 1024 on the big ones. Then the trick I like most. Remember that 262,000 token vocabulary? On the small models, the drafter doesn't score all of it. It runs a top K over clusters of tokens first, so the final matrix multiply goes from 262,000 columns down to about 4,000. 64 times less work in the drafter's most expensive layer. None of this matters if the model doesn't fit. The usual approach is train in high precision, compress afterwards, hope. Gemma 4 trains with the quantization in the loop, so the weights learn to be low precision instead of being rounded into it afterwards. 2 formats ship, a mobile mix, in 2 and in 4 weights with int8 activations, and blockwise Q40 for Llama CPP style runtimes. Numbers. The 31B, 64 gigabytes down to 19.2, that's 1 GPU. E2B, 4.6 gigabytes down to 0.8. That's a phone. And remember all that normalization from the top of the video? A scalar scale on every block keeps activations in range, so half precision inference doesn't blow up. The encoders get the same treatment. The image encoder halves, 400 megabytes to 200, and cuts on-device latency 44%. And the audio encoder compresses 78%, from 390 megabytes to 87, while transcribing better than its predecessor. 4 cuts to memory, 1 to draft speed, 1 to precision. So, did it cost anything? On LM Arena, where humans compare 2 anonymous models and vote, the 31B rates 1451. Top open dense model on the board. 1 generation ago, Gemma 3's 27B sat at 1366. That's 85 ELO in a year. The MOE rates 1438, 13 ELO behind its dense sibling while activating about 1/8 the parameters per token. On the benchmarks, against that same Gemma 327B, MML U Pro 67.6 to 85.2. Live code bench 29 to 80, GPQA Diamond 42 to 84, and the one from the cold open AIME 20.8 to 89.2. That's not a new generation, that's a different animal. And the long context bet, the thing all 4 KV cache cuts were for. On Ruler at 128,000 tokens, Gemma 3 scored 66. Gemma 4's 31B scores 96.4. On Loft, long document retrieval, 8.6% to 79.5. That last one isn't an improvement. That's a capability that didn't previously exist. Now the bit most videos skip. I read this report twice. Here's what it does not tell you. How many experts the MOE has, or how many the router picks. Not stated. How wide the sliding window is, in tokens, not stated. How often the drafter's guesses actually get accepted, the single number that decides whether that whole MTP head is a 2 times speed up or a rounding error. Not stated. How many tokens it was trained on, not stated. There are also no ablations. Nothing in 17 pages says, we tried this and it didn't work. None of that makes the work worse, but if you're planning to reproduce it, you're guessing at 4 load-bearing constants. What it does tell you, data cutoff January 2025, and training spread across up to 12,288 TPU chips, with a scheduler that recovers from hardware failure in seconds rather than minutes. 2 things we only waved at. Thinking mode, a private reasoning trace before the answer, switched on with a control token, and the safety work, which is most of the back half of the paper. But here's the thesis. There's no single breakthrough in Gemma 4. No new attention mechanism, no exotic optimizer, no scaling law. There's local attention, shared values, partial rotation, shared caches, quantized weights, a built-in drafter. Every one of them is a modest win, and they multiply, which is how something that would have needed a server rack ends up in 16 gigabytes on a laptop, Apache 2.0, no API key. And if that encoder-free 12B is a signal, the next generation may not have encoders at all. Paper's linked below. Go read it. It's 17 pages, and now you know which 4 numbers to look for. And if you found this breakdown worth your time, a subscribe genuinely helps. Tell me in the comments which architecture to pull apart next. That's usually what decides the next one.